His methods were systematic but simple. His rewards generally small. More often mud than gold, poverty than riches. But while gold was readily convertible into the cash and comforts of life, the old-time prospector had little use for most other minerals, and neither did the rural economy of his time. Now and then, he did come across important ore bodies, but the enormous wealth under his feet would remain undisturbed for years, until his successor arrived with new keys to unlock it. Today, the geologist is the vital link man between nature in the raw and today's moving scene. The lone search of the past has become a team effort by specialists, hunting minerals in world demand. A hunt that extends over vast and remote regions of Australia, a continent rich in most minerals. To discover these minerals below a surface that may reveal few clues of hidden ore bodies, today's prospectors use electronic probes for eyes, diamond drills for shovels, and computers for dollypots. Machines work and calculate, but men make decisions.
Now it looks as if this boundary here of the decomposed ultra basics marks the boundary with the rather fresh peroxenites. Now, which way did you find the structure to be dipping in this area, John, from your geological mapping?
Yeah, well, these peroxenites are seen
Geologists, geophysicists, geochemists, combining their knowledge to build a three-dimensional picture of a deposit. Beyond their world of anomalies and igneous intrusions lies the ultimate aim of modern mineral exploration, to find commercially workable deposits for the least cost in the quickest time. Having found a likely mineral-bearing area, the claim must first be marked out and lodged with the mines department, a job for the prospector or company agents. The prime target is nickel, but other valuable minerals may come to light during the search, so these are also listed on the form which is filed with the mines department. If the area is available and all formalities complied with, a title is granted to work the claim. After posting on the board, the prospector begins work. A copy goes onto the boundary peg. Where pegging is intense and enthusiasm high, many companies are often involved, and colored tapes help quick identification. Geological reconnaissance can now begin, with surface sampling of rocks, soil, and sometimes plants and water, which are sent for analysis. Thorough examination of the surface is the first vital step in planning a systematic search program. To assist in rapid geological mapping, aerial photographs are used to interpret the surroundings. A stereoscope helps the geologist identify and mark out surface features, such as foliage, outcrops, and other landmarks, saving time and legwork in building up a map of the area. The accuracy of the geological map will depend on precise surveying. Up to now, surveying has only been approximate. Now, a grid is put over the area. Clearing is restricted to the surveyor's line of sight. Each grid point is marked with a peg bearing a coordinate number which is marked on a map. The pegs provide an easily found location for logging geological information or for navigating in a maze of claims spread over an enormous landscape. Bulldozed grid lines mark target areas. The target is nickel and anything else of value. The area within 100 miles of Kalgoorlie, gold centre of Australia. The town that grew up on gold is today the natural centre of the new mineral boom. It keeps its links with the past, its eye on the future. The School of Mines is known throughout the mining world. The bulk of the nation's gold still comes from these mines, up to now the town's only source of wealth. Now, important nickel discoveries in the area have intensified the search for a wide range of minerals. With preliminary survey encouraging and gridding complete, detailed study of a claim begins. Surface sampling, magnetic, gravity and electrical surveys below the surface, through to diamond drilling, the final exploration stage. At each peg, a soil sample is taken to determine any unusual concentration of minerals which could contain nickel. Because some metallic ores and commercially favorable soil types are magnetic, their presence may already be known from government aerial magnetic survey maps, which now cover a large part of Australia. More precise ground surveys are made with the magnetometer, which measures the magnetic differences between possible ore-bearing rock. Readings are taken at each peg, and from the information compiled, a magnetic contour map is prepared. In the hunt for nickel and base metal ores, magnetic and electrical devices have proved the most effective for Western Australian conditions. Sulfide-bearing minerals are good electrical conductors. Today, the most important tool used in their detection is induced polarization, IP. Electric current injected into the ground will flow through any conductive material it meets, such as pockets of salt water, making electrical probes sometimes unreliable. But IP is unaffected by such conductors and largely depends on metallic sulfides for good electrical response. From the transmitter, leads are taken out along the grid line. While at another point, a receiver station is set up. Aluminium foil electrodes are buried in shallow trenches. The water helps conductivity. Other electrodes, copper sulfate in porous pots, are linked to the system. With the circuit complete, a charge is transmitted. Contact forces redistribution of ions over the rock surface. Current is switched off and the decayed current or polarization measured. The better the response, the closer the probes, until the length and shape of a suspected ore body is recorded. Generally, no response means no sulfide body. To help in locating ore bodies, a gravity meter is sometimes used to measure comparative rock density. All this field information must be processed and translated into geological maps and graphs for presentation to the client. An exacting job, taking time and patience. Geochemical sampling continues all through an exploration program. Vacuum drills are useful in soils and soft rock, and their mobility makes for rapid sampling. The samples are carefully blended and made up into 2 lots, one for reference and one for the laboratories. In harder rock, percussion drills are more effective. Samples are blown up from the drill hole and collected from a cyclone. In the labs, physics and electronics take over from the geologist. Soil and rock samples, as well as drilling cores, come here for analysis, providing information the geologist will need for the next stage of the search. Geochemistry, unknown at the beginning of the century, is now an essential science in finding ore. Progress in the labs has speeded up assaying of soils and rocks enormously. Work that once took hours now takes seconds. Other equipment detects and measures particular minerals, in this case, sulfur. From computers come more assay figures for interpretation and mapping. Short of actually handling a sample, all that can be learnt about the deposit is now known and forms the basis for the next decisive decision.
Now, I think that in view of all the facts that we have before us, that we should drill 500 feet north of this line here. And that would put it there. Good.
To have reached this expensive last stage, each step will have been more encouraging than the last, leading up to the final act of a successful affair with nature, diamond drilling. The aim is to find thickness, quality, and inclination of the ore body. To achieve this means gathering new information from each drill hole. Because some deposits dip steeply, the drill is inclined in the opposite direction to hit the target. The use of water pressure helps to avoid breakage and keep the core intact for easy examination. The drilling depth of each sample is carefully recorded as it arrives, so the geological map will be accurate. After a cursory examination by the geologist, samples are rushed to modern laboratories for analysis. Cores are first split into two sections, one being kept for reference. Samples are crushed, ground, and passed on for analysis. Powdered material is melted in crucibles and fused into discs, suitable for analysis in computers. Statistical analysis provides a rapid feedback of information to the geologist and client, so decisions can be taken quickly, without loss of time or money. And finally, the end product of a long and exhaustive search involving specialists in months of work, translated into information that will reveal a new mineral field to create new mines, roads and towns of the future. The client's report can affect many lives. A new mineral discovery means new capital, new companies, bringing new sources of revenue from overseas, expanding industry at home, demanding more people, more skills, and more development. Industrial progress, the key to better living standards and higher cultural attainments, depends on a continuous supply of minerals that flow from a search that never ends.